Hi, everyone. So my name is Diane, and today I'll just be talking about how we ended up converting some of our existing critical workflows to Temporal and some of the phasing approaches that we took to get there. So a little bit about myself. I'm from Atlanta, Georgia. I work for a company called Linus Health. They're headquartered in Boston, Massachusetts. I've been with Linus for 2.5, almost 3 years at this point. And as a software architect, I've worked on technical roadmaps. I've driven multiple projects in our ML and product engineering departments. And I've also done a lot of hands-on design and implementation, even though my title is architect. I'm exposed to a lot of workflow-centric things day to day on the job, just all the time, especially around our bidirectional third-party integrations in the EHR space. So putting things in the medical chart. And then also our complex analytics processing pipeline. So quick agenda, I'll be going over our use case for Temporal at Linus Health. So this is basically just a quick summary of my presentation from last year. And then I'll talk about how we ended up redesigning our current workflows against Temporal, as well as tooling exploration. So we did mess around with like 3 different SDKs from Temporal before settling on Java, as well as operationalization around team structure, integrating Temporal with our broader platform, and also our journey to Temporal Cloud. And then I'll sum it up with key takeaways. So why Temporal? Before I get into the actual why, I feel like I should probably give like a quick summary of what Linus Health does. So we are a digital healthcare company. We are focused on transforming brain health for people across the world. So our cognitive assessment platform enables earlier detection and intervention of Alzheimer's and other dementias. Traditional pen and paper tests, as well as hands-on proctoring sessions, are digitized, resulting in sensitive and efficient workflows for both medical providers and clinical researchers. We also provide actionable insights based on analyzed results from these tests to help inform next steps for the patient. We offer several different types of tests, but one of our flagship products is the DCR assessment, which stands for Digital Clock and Recall. So it's composed of smaller, isolated test segments where the patient is required to draw an analog clock and then repeat back a list of words immediately and in a delayed fashion. So data is collected from these test segments and analyzed. Once all the results are gathered, an event is raised to indicate that results are ready for downstream components. So these downstream components are categorized under post-processing, which includes displaying results for the patient in our front-end applications, as well as shipping out these results to the patient's medical chart in their EHR. Our use case for Temporal is all of the workflow orchestration that facilitates our analytics processing pipeline. So this is a very simplified picture, so I'll just break it down even more. Our legacy processing pipeline consists of a bunch of event-driven AWS Lambda microservices that are orchestrated through SNS and SQS routing from Amazon. The pipeline gets triggered when the patient begins taking the DCR assessment. This results in an API call into our platform that generates a result data model, which outlines the components and type of results to expect as part of this patient's test session. The pipeline at this point is waiting for data to become available. So what this means is that as the patient is completing each test segment, raw data is uploaded for that test segment, and the segment is marked in our backend as ready for processing. The pipeline gets notified that data is ready to be processed, so the relevant engines begin processing that raw input data. We have an engine for every test segment, so this means there is a clock engine, immediate recall engine, and delayed recall engine that are all computing result metrics. There's also another engine out there that's not necessarily analytics, but it basically takes the raw input clock data and generates artifacts to display in our reports later. And then the results from the clock and recall engines are gathered as input into our DCR engine, which computes metrics for the entire DCR assessment. And then once that's done, the output of the DCR is fed into another engine to check if there are any clinical concerns based on the DCR scores. And then from there, the pipeline raises an event to indicate that all results are ready. So front-end portal views on our web and mobile applications, EHR integrations, and reporting artifacts can then begin displaying these results. There's also some other things happening behind the scenes here during results processing, such as various external service calls, as well as persisting different discrete results to our database. This diagram looks clean right now, but it's actually quite messy in reality. So there are a bunch of arrows between all these different components, and there's not really a standardized pattern here. The routing is completely custom and defined by distributed queues and any dependencies used by our analytics engines. This is a very big oversimplification, but imagine the number of arrows here being the number of engines times the number of their dependencies, times the number of assessments we offer to our customers, times our growing customer base. Another call out to make here is the fact that even though the result data model that got created at the beginning of this pipeline contains all the components that are required for processing, none of it is actually declarative and directly used in the pipeline. So this legacy pipeline became very difficult to maintain over time, especially as we introduced new tests for our customers and consequentially new analytics engines. So whenever there was a production issue, debugging was too time-consuming and required a ton of manual engineering involvement. There were bottlenecks in certain steps of the pipeline because of how it was designed. Automatic retry and error handling weren't really a thing, causing our pipeline to be extremely brittle. And there was no concept of a pipeline run either, even though a patient could take multiple tests in the same clinical session. Versioning and data contract standardization were also not enforced, causing huge deployment headaches for our engineering organization. So we decided to redesign our processing pipeline with Temporal in mind. I called out earlier that we were not using our result data model effectively. So in version 2 of our pipeline, the result data model is actually declarative and defines required pipeline components at runtime. It is fed into a generic parent workflow for a processing pipeline as the workflow input, and then child workflows are dynamically generated based on what is defined within the data model. This diagram is a bit of a reverse of what the legacy pipeline looked like. So instead of triggering the clock and recall before the DCR, we're doing the opposite here because it just makes way more sense. The parent workflow needs the results of the DCR workflow in order to review any clinical concerns, and the DCR workflow needs the results of the clock and recall workflows in order to compute the DCR score. Dynamically defining our workflows at runtime highlights the fact that we achieved a data-driven workflow execution, which enforces modular design and flexibility as we change requirements over time. I mentioned earlier that the pipeline spends time waiting for raw data to be available before it can get processed. We can basically accomplish the same thing here using workflow timers and signals. So as these workflows spawn, a timer starts because we don't want these workflows to wait forever to receive data. If the timer expires before any data comes in, the workflow will end gracefully. If the workflow receives a signal before the timer expires, then it will begin processing that data and call the relevant workflow activities. Signals are emitted whenever raw data is uploaded from the patient's test segments. So conceptually, this part doesn't change. In our legacy pipeline, whenever raw data was uploaded for a particular test segment, that raised an event to tell the pipeline to begin processing that raw data. We just changed the implementation here and replaced those events with temporal concepts, so signals. We also want to continue to raise the results ready event because even though we redesigned the processing pipeline on temporal, post-processing components still need to rely on a raised external event to begin their work, and none of that is ready for temporal yet. So here's a closer look at how we designed our child workflows. So instead of having arrows go back and forth between our engines and shared service components like API calls and persisting to a data store, we converted those into activities with workflow boundaries. So each workflow for a particular test segment can now operate independently and in parallel without causing bottlenecks with each other. So not only does this provide better stability from an architecture perspective, but it is also useful for emitting partial results. So our customers want partial results for a patient's test, and it was impossible to do that with our legacy architecture. So result generation at the time was basically an all or nothing deal, where if one step in the pipeline broke and failed to process something, there would be no results available at all for that patient. And In the real world, for example, a doctor may still want to know a patient's clock drawing score, even if their delayed recall score is not available. This is just another view of how we designed our parent-child workflow relationships, but now fanning in the results at each level. So the DCR workflow waits for all of its children to complete in order to calculate the overall DCR metrics, and then the main parent workflow analyzes the DCR metrics to determine any clinical concerns for that patient. Once done, the main parent notifies post-processing components that results are ready. To enable this workflow design, we also had to design the building blocks, which are the temporal activities. We took inventory of all the processing steps within our pipeline and determined the scope of what a temporal activity should represent. So at the end of the day, an activity is just a pure function that serves a single purpose. We took this concept to what we already had, which consisted of analytics engines, external API calls, and artifact retrieval and generation. For example, the execution of a specific analytics engine should be a temporal activity. If an artifact needs to be fetched because it's required as the engine's input, that artifact retrieval would constitute another temporal activity. Solidifying our building blocks was a critical path dependency for implementing our temporal workflows. We knew that after taking inventory of all existing processing components, some refactoring had to be done before these components could be converted into activities. So our engines are written as Python libraries by our data science team, and in order to deploy them, we had to write thin wrapper code around these libraries and deploy them as Lambda functions. However, a lot of these engine libraries had external dependencies co-located with the bespoke engine logic. So for example, the recall engine made an external API call to a transcription service to get the transcription result before actually beginning analytics processing. Ideally, the transcription service call and the bespoke engine would be separate components. And then to ensure backwards compatibility while not deploying duplicate engine implementations for legacy and temporal, we decided to introduce a common abstract wrapper implementation that allowed these engines to be invoked the legacy route, so through SQS processing, and also the direct route, which is through a temporal workflow. There's also a huge lack of standardization on payload formats for these engines, so we enforced data contracts for expected inputs and outputs that were also shared with non-engine consumers, such as workflows that are responsible for actually invoking these engines. So as I mentioned in the previous slide, some of our engine libraries had to be refactored. So here's an example of bespoke analytics engine logic being tightly coupled with external service calls within the same code base instead of being broken apart into distinct components. By redesigning this with temporal in mind, we pulled out these external dependencies into their own separate components while isolating the core engine logic. So some of these external dependencies can also be executed in parallel rather than sequentially, which was not possible in the legacy code base because everything was combined as a sequential single-threaded design. We were also intentional with how we designed our temporal workflows because we wanted to maintain a data-driven approach where workflows could be dynamically created. We wanted to implement a generic standard for our pipeline components, and we knew all pipeline components required some sort of artifact input as well as a processing method. So here we defined a generic pipeline component interface. So in the context of the immediate recall test segment, which contains multiple components like audio normalization, audio transcription, and the actual recall engine logic, each component would implement this interface. And then from there, we can generically wrap each pipeline component as a temporal activity. We also took the generic approach when it came to defining the workflow. So we basically divided a generic parent workflow and a generic component workflow. So the main parent is what gets executed when the patient begins taking the DCR. The result model containing all of the declarative pipeline components gets fed in as the workflow input. So we've also got a generic signal method that receives uploaded resources and notifies child workflows that are waiting for those resources. So things like uploaded metadata for a test segment or uploaded raw audio files. And then for our child component workflows, this is scoped to our pipeline components that we previously wrapped as temporal activities. This is where the bulk of the processing of the pipeline is done. where we declare what inputs are required up front prior to executing the activity, and then we take the output of that activity and persist it into our storage layer. The signals that the parent receives also gets forwarded to the relevant child component workflow. This is what the parent workflow implementation sort of looks like. It's not super accurate. I removed a bunch of code and renamed some things, but it should give you a high-level idea of how it works. And then you can see here that based on the input result model, we are parsing out all the required components that basically determine which children to execute at runtime. And since we're creating child workflows on demand, we also want to make sure we avoid any zombie workflows in case the parent terminates and we still have child workflows still running. And when starting a child workflow, we also incorporated a handler to notify other running children workflows about the resources this child creates. So this is important because we have some dependencies between our pipeline components. For example, before the audio transcription component workflow begins processing, it needs to wait on the audio normalization workflow to complete and produce an output artifact first. So we explored a variety of tools at the beginning of our project into Temporal. We did a quick POC with the Python SDK because we thought we were going to make a Python workflow monorepo since all of our analytics engines are already written in Python. And we also thought about co-locating that code with the workflow code directly as activities. We defined our workflows as classes and also leveraged Python's async IO library for signal handling. We also looked into PantsBuild, which is a monorepo tool that has a Python-first approach, but we ended up scrapping this project because all of our Python engines were not standardized on common dependencies, so dependency resolution was a nightmare. PantsBuild also relies on dependency inference, which does not work well for complex code bases. We also did a TypeScript POC, only because all of our product engineering teams use TypeScript and JavaScript. TypeScript was interesting because the workflows are typically defined as functions instead of classes compared to the other SDKs we've used. And there didn't seem to be a super simple way to annotate them like the Python and Java SDKs. We used Rush for monorepo tooling, but it was primarily created to publish NPM packages. So custom plugins had to be created to do anything else like Docker image builds and integration test setup. We ended up dropping this because we already had some internal gripes against using TypeScript and JavaScript for backend processing at our company. So we ended up settling on Java because it addresses known pain points we already had with Python and JavaScript, so things like concurrency thread handling, verbose exception handling, code profiling. And we also already happen to have engineers with Java experience. We also wanted to leverage the idea of dependency injection and inversion of control to align with our desire to have data-driven workflow executions. And that's more of a common pattern with Java. Our use of the Java SDK leveraged workflow and activity interface implementations, as well as Spring Bean components for the activities. For local development, we just use the Temporal dev server. You can do Docker Compose or do like the all-in-one binary. It doesn't really matter. And then also local stack to simulate AWS resources since we are a cloud-native shop on AWS. So as we continue to implement this project, we also had to define areas of ownership since we had to reshuffle some of our architecture. Analytics engines will continue to be owned by our data science team. Processing pipeline components will be owned by product teams that need them because they're the ones who understand the business logic. The way we structured our code base abstracted pipeline components from Temporal, so allowing a typical product developer to not really care about Temporal when writing new components. The actual workflow and activity code will be owned by the workflow team. I say workflow team, it's technically the medical devices team, but like for the sake of this presentation, I'm just gonna call it the workflow team. And then for worker service deployment, that is a collaborative effort between the workflow team and our DevOps team, which also includes Temporal Cloud integration. As for workflow clients, which facilitates when to execute and signal these workflows, we decided to open those up as API endpoints. So the idea is to have the workflow code and worker live inside of a RESTful service as a Spring Boot application, and existing external components can still call into the service to start or signal workflows. At the beginning of this presentation, I mentioned that there were two main external interactions with our workflows, which is when the patient begins their tests on the mobile app and when the mobile app uploads data during their test session. Those interactions will still exist, but they will be modified to instead use these new APIs. And then as for Temporal Cloud, again, this is more like a rehash of my presentation last year, so I'm not going to dive into this too much, but last year we set up the capability to use Temporal at Linus by deploying infrastructure elements to support Temporal Cloud workers. This involved certificate, key pair, and namespace creation, a pattern to build and deploy ECS worker services because we host things on ECS and not Kubernetes. Custom encryption codecs, leveraging our own encryption keys, so basically the custom data converter implementation, and logging from our workflows and activities to Datadog. We also created custom search attributes for our component workflows to align with logging attributes that we already send to Datadog. So we broke out our implementation approach into phases. The first phase was to crawl and figure out what actually needs to happen and address architectural dependencies. This included revisiting our data models and refactoring our engines. The second phase involves implementing the actual workflows in parallel with our legacy architecture and fully vetting our ideas. The goal is to compare accuracy of our results, performance of the new versus old processing pipeline, and gains in workflow visibility and traceability. We are in the middle of this phase right now. And then once that's done, we can start running and start fully migrating our workloads to Temporal. So our main takeaways from this project was that we had to build a strong use case for Temporal to get approval to go work on this. A lot of the pre-work involved presenting the value proposition of what we would gain from Temporal and how that would fix our problems. So it boiled down to developing a business case, gathering metrics around operational burden, and customer impact with our legacy architecture. Also, this is just a general architecture best practice. But before taking on a big project like this, always take inventory of your dependencies before you start building. This will help solidify design requirements and implementations later on. We also did not want to take on a bunch of work with Temporal at the first go, so we defined the scope of the project instead of attempting to tackle every problematic workflow within our platform, because there's a lot. It was a balance between finding the most critical workflows that were also simple enough to implement with Temporal in a reasonable time frame. Lastly, we also had to think about doing a transitional approach versus a hard cutover approach and what downstream effects that would have in the rest of our platform. And that's it. Any questions? So if I understand your question right, the short answer is yes. So like we have other like low-hanging fruit that we can tackle with Temporal, like our EHR integration workflows, where like one of the core things that we integrate with is like when a clinician places an order on the patient's medical chart, we pull an external task queue owned by the vendor to get that event, do something in our platform, and then send back results. It's actually a very, very simple flow, but that's not super high priority. We have way more customers using like our core platform processing. So like every single time we sell assessments or cognitive tests to a new customer, this processing pipeline is always going to get used. So there's just a lot of traffic there.
So also the V1 choreographed sort of workflow, it said Q was a function of many different factors. I imagine those didn't just magically go away.
No. Not really. So sorry, I'm just trying to. Okay, so I would say that like the main takeaway from all these arrows that I'm pointing out, it's not the level of complexity, because I don't think the amount of complexity is necessarily going to go completely away once you move to Temporal. Because there's still going to be orchestration elements. The fact is there's a huge lack of visibility in V1, So if something broke here, it would take an engineer several hours to actually figure out why it broke.
Were the engineers properly trained on log insights and things of that nature?
No.
So they would literally be, it's a murder mystery. And
Yeah.
They're a deer in headlights.
Yeah, and like, that's like another issue with startups too, right? So like, everything is kind of ephemeral at the end of the day, so there's a lot of tribal knowledge, and some of that knowledge does go away when someone leaves.
How was the test coverage?
The integration tests are terrible because of the lack of standardization. I could give a whole talk about what's wrong with our analytics engines, but I'll save that for later.
So there's all sorts of interesting things here, like the retry logic, for instance. I imagine your queues had retry policies, and you had dead letter queues
Yeah.
and so forth. And maybe they programmed these in an idempotent fashion, maybe not.
Yeah, so we did have we had default retry policies on the queues, and there were dead letter queues, but like even then, it wasn't super reliable. Like there was also lack of like robust error handling, like exception handling and retry logic within the actual code base. So one example is, this isn't a Lambda function, but we have another complex analytics engine that runs in a container service. It didn't implement like basic things like a health check, even though it was still listening for events coming from a queue. It was like, there was just so many things wrong with all these little boxes.
And then were you using like CloudWatch alarms, so when a Lambda error happened, an alarm was triggered?
Yeah.
Slack, whatever.
Yeah, so we actually integrate, I think we just forward stuff from CloudWatch over to Datadog, and then we set alerts from Datadog, and then it just forwards things to Slack.
Okay, but even with that, it was still a murder mystery.
Yeah.
Curious if you ran into this problem when you first started. So we have a team that runs a workflow engine and has like hundreds of workflows in it. And they said they looked at Temporal, but it seemed very interesting. They could address a lot of the problems, but they don't want to have to deal with running two workflow engines at the same time, right? Like say they have 100, they start even like starting a new one. It's like, well, now we got to look in two different places, two different workflow engines, and we don't want to deal with that. I'm curious if you kind of ran into those kind of problems.
So we're actually going to be running in parallel. Like I said, like we're literally in the middle of implementing this right now. So the DCR specifically, we're going to run it in parallel because we already have a bunch of customers using DCR, and we don't want to mess with downstream things like reporting artifacts that we're sending to their clinical providers. So we're basically just dumping the metrics to an isolated database that's not our core platform database. But we do have a strong use case for using Temporal for like a net new workflow engine that's backing a new assessment that's coming in Q4. And because it's net new, there's like less like complexity around having to deal with what happens, like if this interferes with something that already exists, because nothing already exists for it.
Can you talk a little bit about debugging in the old system and how it will look like in the new system?
Yeah, so debugging the old system, you couldn't even see what type of inputs and outputs were coming out. Like that, it was that bad. Like at least with Temporal, you have event histories, so you can see like the payloads that are getting sent to your activities and workflows and what's coming out. And also, depending on what activities you have in a given workflow, you can literally see what steps in that workflow are getting executed. In this old paradigm, we didn't have anything like that. Like it was mostly just like, so like you had to be an engineer who was already familiar with the architecture to understand like what the next step in the pipeline was gonna run. But like the logs were pretty bad. So yeah, I don't know, debugging's like pretty bad.
So then to follow up here, since you're kind of leaning pretty heavily then on Temporal's observability infrastructure, I'm wondering how you are supporting it for like just additional insights if you need it.
I don't know yet. So we do have plans to implement some like SDK tracing, but we haven't made it that far yet.
I was curious, you talked about exposing two different handlers for the same generic wrapper.
Yeah.
And I was curious to hear a little bit more about that. I don't understand the system that well, but I was curious if that extra exposure was any sort of additional security risk or just architectural risk.
So this is mostly for backwards compatibility, and the abstract handler that I was talking about, that's basically wrapping around the engine code for 2 different paths. That's all code-based. So taking a step back, our analytics engines are literally just like shareable like Python libraries, and in order to deploy them into actual components in our platform, they're hosted on Lambda functions. However, those engines have to be wrapped like with some other abstract implementation, and for V1, it only assumed SQS invocation. Like you didn't really have a good way of directly invoking the engine wrapper with just the expected engine input payload. So we allowed parallel paths because, again, DCR is already being used by our customers. So in order to not break things that might be leveraging this, we wanted to do 2 parallel paths. So like it's still the same Lambda function, but you have the option to either invoke it with a queue message or literally just directly invoke it.
So the queue invocation is asynchronous. The direct invocation is synchronous. Does that cause any weirdness?
Not really.
Not really.
Not with what we're doing.
I guess in your workflow, will you go back to the new workflow slides? You mentioned a lot of this was had atomic transactionality. It looks like synchronous communication. Like so these are lines of dependency, right? Where parent is dependent on
Yeah.
DCR dependent on clock. Okay, and then this is synchronous communication where DCR requires a response back from clock before it proceeds
Yeah.
to immediate, or are these also concurrent workflow executions?
Yeah, so clock, immediate recall, and delayed recall, they're all executing, well, technically DCR. I didn't really paint a good picture of this, but technically all these child workflows, except for the parent workflow, they're all running in parallel, and they're literally just waiting for inputs to be available before the actual like processing method gets invoked.
Okay, so then does DCR need a response from all of these before it completes?
It's not really a response. It's just boiling down to input and output artifact dependencies. So it's not like it's directly spawning the clock and immediate recall and delayed recall workflows and waiting for those workflows to exit and return an output.
So it's not synchronous.
It's more like, so for example, we know that a DCR needs output from the clock to do processing. When the clock workflow finishes computing its metrics, it saves the output artifact to a storage service, and that actually forwards a signal. So the DCR is basically just waiting for signals to declare that these inputs are already available, so it can begin like calculating the DCR scores.
Do all these have their own isolated data stores?
No. It's mostly just like segregated by tables and name spacing schemes, like earn schemes, where like.
Had any challenges with these concurrent processes fighting for database contention?
In the old pipeline, yes, because like any single time you were writing out metrics, like something had a lock on the database, and then we would just get false errors alerts, even though it would retry again later and be successful. This one, again, we're still in the middle of implementing this, so we haven't necessarily run into that yet.
And then finally, when an error does occur in one of your workflows, are you capturing that and publishing it to Slack or triggering an alarm?
Yeah, the goal is yes. Yeah.
Yeah. Are you creating like a bespoke way of doing that, or is there any kind of standardized tools you found within the community?
I would say TBD.
Yeah. Fair enough.
I guess taking a step back, you guys are re-architecting something that was developed as a startup was growing.
Yes.
And I guess Temporal is kind of the thing that you're using, it's like the crystal, I guess, to build everything right.
Yeah.
If you weren't using Temporal, do you know what you would be doing? Or would you?
We would probably have to either roll our own state machine, which comes with its own complexities. We've also looked at Cadence, but that was before we thought we were going to use. That was before we realized we were going to use Java. Like we originally thought we were going to use Cadence, which was like the precursor to Temporal, but I think it only had to go in Java SDK. And at the time, we were like, okay, we're going to write in TypeScript. So then we moved to Temporal, but I don't really know the difference between Cadence and Temporal. We've also explored step functions. That was a horrible idea, by the way. Like, I don't like step functions. Simple workflow service is also great, but again, that's like super old. I think it's technically no longer supported by AWS. But like the main reason why we settled on Temporal, it's not because it's like an amazing workflow engine, which it is. It's more like you don't have to worry about actual state management. which is the most complicated part of it when it comes to developing a workflow engine.
Have you had any challenges with the determinism or the idempotency of designing your workflows?
Yeah, so for these engines specifically that I talked about, no, but like in the realm of EHR integrations, where eventually we do want to use Temporal for EHR integrations, it's definitely not idempotent, because like you're literally like integrating with a third-party system and you don't know what to expect. But we haven't really come into issues with that yet because we haven't implemented.
What kind of things do you expect?
Sudden breaking API changes because some of the vendors we work with just change how their APIs work without notifying their customers, and then it breaks a bunch of stuff. Or timeouts that we have no control over, or like in the case of like where you're pulling external queues that aren't owned by us. For some reason, there's a rate limit that like that the vendor all of a sudden changed and we didn't know about until a day later when production exploded. So, yeah.
Have you experienced any kind of strange sort of coupling that you didn't foresee? For instance, the DCR workflow is coupled with the clock workflow here, when the clock workflow just goes down, and now the DCR workflow just can't proceed because it's not receiving the signal.
Yeah, so like at that point, this is where the idea of, where was that slide that I had about partial results? Like this is where it came in. Like we still, like in case the clock workflow doesn't finish, but we still have like these two other workflows that completed successfully. Obviously the DCR workflow is not gonna compute because it's missing some, like the clock metric, but we still wanna like output these distinct separate results. So we do have to account for like error handling if a child workflow fails to return something. But at the end of the day, like our main priority, especially with our customer base, is omit anything that was completed at all partially, because doctors at the end of the day will want to care about that.
Did you know that you had an eventual consistency sort of service level objective with your customer, and you just kind of naturally put yourself into an atomic consistency state with your old
Nope.
pipeline?
Nope.
Yeah. It's interesting.
So you talked about how you're like currently in implementation and you've got kind of a split brain situation where you run a bunch of workflows twice, or you've got like some subset. What's your game plan for turning the old thing off?
Feature flags. I've been wanting to move off of like the old architecture for a while, but again, it's a startup, right? Things move fast. We always have shifting priorities coming from top down from leadership. And the problem is, we've been trying to get something to production for Temporal for over a year now. But there's a lot of requirements coming down where we have to keep building more and more and more assessments to sell to our customers. And all of that has been on top of the legacy architecture. So like the plan for DCR is do it in parallel, but we have another big project that's coming in Q4 that's only gonna use Temporal. It's not gonna do this parallel stuff that I talked about for DCR. That's gonna be backed by a feature flag. So basically, if it's this type of assessment that this patient is taking, just immediately pivot to calling those APIs from the new Spring Boot app that contains our Temporal workflows.
Have you considered?
Oh. Yeah.
I assume the nature of the data is sensitive, that's PHI. So
Yes.
was there any difficulty dealing with that as you were building?
Not really. So we actually signed up for Temporal Cloud before they became HIPAA compliant. And in order to work around that, we just implemented a data converter. Because it integrates with our own encryption keys, so like data is encrypted end to end. And then we also implemented something called a remote codec server, where if you are debugging something in the event history or looking at inputs and outputs, like in the Temporal Cloud console, you literally just like put a link to where your codec server is. And that codec server is self-hosted by us. Like Temporal doesn't have access to that.
In terms of auditing Nguyen has seen the traceability, just look to Temporal Cloud to get that audit done.
Yeah.
So back to what you said before about challenges in migrating from your old system to your new system. Have you tried to do a sort of event interception and asset capture, like a systematic little capture pieces of the architecture? Or is that, do you find that that's just really infeasible, given if you're going to switch to this orchestrated workflow engine, you have to switch to the entire thing? Or?
So we're definitely breaking it apart. That's why I said that like there still has to be an external event raised to signal like post-processing components like reporting that the workflow is done. None of that is going to Temporal. So like we're literally just like segmenting pieces of our platform to use Temporal. And we thought about decoupling it too, like with an event bus, because we don't really have an event bus right now. But the plan was to use that like in between like the temporal stuff and the non-temporal stuff.
You're using SNS and you have topic filtering, so you can technically do sort of like event bus.
Yeah, but like it's a pain to manage, you know, because like it's still like different topics at the end of the day. Where event bus, you have like one central thing, and you can just define specific event contracts for your consumers and producers. So it just makes like management overhead a lot easier when you have like one central thing to worry about.
What's preventing you from doing that? Because you can use EventBridge with rules and
Yes, I know. We recently came out with like a direct-to-consumer API service, and that uses Event Bus. And the only reason why it uses Event Bus because the architecture team was responsible for it, and we wanted to do things the right way. The main reason why we haven't used Event Bus for our existing platform is political barriers for some reason. Like the higher ups just didn't want to use EventBridge. I don't know why.
yeah, that's frustrating.
Yes, yes it is. I'm a little hungry, so.
The other mic. I have to take over MC duties.
Okay.
I really feel bad cutting off this great Q&A because you were clearly incredibly engaged, but I just heard our speaker and my own tummy get very hungry. So thank you all very much for coming here. Let's give Diane another round of applause.